Hello there. This lecture is going to show you how to make sense of large amounts of data by showing it in a table or showing it in a graph. And really the heart of this lecture is figuring out how to do those things for a single variable. There'll be a separate lecture that'll show you how to do that for multiple variables or for variables where you've collected data across time. But for this particular lecture, I really want you to focus on how to interpret the graphs and tables, and also how to understand when to select which table or graph to display your data based on the nature of the data that's collected. You'll get an Excel video that'll show you how to create some of the tables and graphs that you'll see in this lecture. But for now, focus on understanding the content and deciding when it's best to use which type of table or graph. So specifically in this lecture, you're going to learn how to understand frequency distribution tables and also histograms and bar charts that go along with those tables. And again, the decision of which to use, a histogram or a bar chart, is going to depend on the nature of the data. So through this lecture, I'll show you how to make those kinds of decisions. Then I'll also show you how to construct relative frequency distribution tables, or in other words, just looking at percentages instead of raw frequencies. Then how to convert those into pie charts and understand those. And then we'll also look at grouped frequency distribution tables, which allows you to display data with a wide range of values without having a row for each specific value in your data set. So although I'm not going to have you construct frequency distribution tables by hand, it's important that you understand how the raw data translates into a frequency distribution table. So here you'll see both. You'll see all the raw data right here, and then all of that raw data is really represented in this table right here. So the way that a frequency distribution table works is you display the full range of values from lowest to highest. Typically the lowest is at the top, and then it goes all the way down to the highest at the bottom. Now, it's really important to note that for a true frequency distribution table, you want to have a row for every single possible value between the highest and lowest scores. So for instance, if we look in this data, you can see 0 is our lowest score and 5 is our highest score in the data set. Now, even if, for instance, there were no 2s here, you would still want to have a 2 represented here. So you want to have the full range of values from lowest to highest, even if the frequency for some of those values is 0. But in this case, we actually do have some 2s. But again, even if we didn't, you'd still want to have a 2 right here, and it would just say 0 right here. So if you look at this and you do it on your own, you could see that there's 5 zeros, right? So how many zeros? There's 5. There's 8 ones. There's 14 twos. There's 13 threes. There's 6 fours, and there's 4 fives in this data right here. So when you look at this raw data, it's probably hard to make sense of it. But once you convert it into a nice little table, you can see the trends more easily. So here you've got all of your values, or X. Here you've got how many times those values occur, or your frequency. So with this table, it's much easier to answer a question about your data. So for instance, how many iPads should be in stock on a particular day, right? So we're looking at, these are all the number of iPads sold in the past 50 days. So each number represents one day, and there's 50 numbers in total. You could check that by adding up all of these values, and the sum of the frequencies would be 50. There's 50 days. So how many iPads should be in stock on any particular day? Well, if we look at this, we can see that on most days, we sold between 2 and 3 iPads. So you'd want to have at least 3 to be safe, but you can see that it goes up to a maximum of 5, so maybe have 5 plus on hand just to be extra, extra safe. So hopefully by looking at this, you can see how this turns into this and understand the usefulness of this table as opposed to just looking at a ton of raw data in front of you. So now that I've showed you how raw data can become a frequency distribution table, I want to show you how you can use a frequency distribution table to make some math a little bit easier. So if we look at this, again, I already showed you that you could add up the total frequencies to get your sample size, which in this case is 50 days. There's 50 numbers up here. But let's say that you wanted to know how many iPads were sold in 50 days. So as opposed to saying, okay, what's 4 plus 5 plus 3 plus 2 plus 3 plus 1, all those numbers added together, you can use your frequency distribution table by taking your X, right, the actual value, how many were sold, times the frequency, how many days did you sell that many, to get these values here. Then you add those values up, and you can see that over the course of 50 days, we sold 119 iPads. So that's your sum of X, your sum of all of the numbers added together. And this is nice because you don't want to have to add all these numbers up. And sometimes you're not given raw data. All you have is a frequency distribution table. So sometimes you may need to know the total number of items that you looked at. And whenever we get to looking at measures of central tendency and computing the mean, to do the mean, you need to have the sum of X divided by the sample size. So in this case, our sum of X would be 119 divided by 50. And let's see, what does that give you? Not about to do that in my head. So let's see, 119 divided by 50, 2.38 would be the average or the mean here. I'm not going to have you do that yet, just to show you a way that you can use these calculations in the future. So now that you've seen data presented in a table form, I want to show you how to take that table and convert it into a nice, pretty graph. Most people prefer, the visuals of a graph over a table. So before we look at different types of graphs, I want to kind of have you understand the mechanics of a frequency distribution graph. So the first thing I want to talk about is the x-axis. And in any kind of graph, your x-axis is down here. That's your horizontal axis. And the way this works is you plot the values for your variable, for instance, how many iPads were sold, from lowest to highest, left to right. So low to high, left to right. So again, this would represent all the different values in your data set. Then the y-axis, or the vertical axis, wasn't anticipating that second bullet there. There we go. That represents your frequencies, so the count. So if you think about it, histograms and bar graphs, the two that I'm going to focus on the most, the height of those bars is going to tell you the frequency associated with each value. And this is going to go from low to high, bottom to top. It's also important to note that typically with the frequency axis, you want to start at a 0. But for your x-axis, let's say that the lowest value in your data set is nowhere close to 0. You don't want to start with 0. So I typically have people, and I do this in practice, you start with the lowest value in your data set and then go to the highest value in your data set. Don't be inclined to start with 0 because that's going to mess up the shape of your graph. And I'm going to show you different shapes here in just a second. So now that I've explained the mechanics of frequency distribution graphs, I'm going to show you a couple of different commonly found shapes of distributions that you see in the business world and in psychology and just research in general. Now remember, we're measuring all these values right now at a single time period, not necessarily changes over time, but you can also have different shapes of distributions when you're measuring variables across time. So just remember, the x-axis goes from low to high, left to right. The y-axis goes from low to high, bottom to top. The x-axis represents all the different scores found in your data set. And then the y-axis represents how often or how frequent those values are in your data set. So the first shape I want to demonstrate is the normal curve. And this is a situation where the bulk of scores fall kind of in the middle. And then you have extremely high and extremely low scores that are less frequent. And the way that I know that these extremes are less frequent is if I go to see where they fall on this frequency, they're on the low end, whereas these scores in the middle are very common, very frequent. So some examples of things that are normally distributed in the world would be performance. So typically, most employees kind of fall in the middle in terms of performance. And then you have some rock stars over here and some duds over here that aren't really doing their fair share of the work. Another cool example of a normal distribution are stock returns. And if you click this link down here, you can check out this really cool interactive demonstration of stock distributions with the percent return on the x-axis and then the number of years with that return as the frequency. And you'll see that consistently all the different portfolios that are available to kind of play with are normally distributed. Now let's take a look at a different type of distribution, the rectangular distribution. So this is a situation where all outcomes are equally likely, or in other words, you have the same frequency for each particular value that you could have in your data set. So this one is rare, with the exception of like decks of cards. So like for instance, you have an equal probability of drawing a heart, a club, a diamond, or a spade because there's an equal number of those different suits in a deck of cards. A coin has a uniform distribution too because the probability of getting either heads or tails in a toss is the same. So this is a more rare distribution when you're not really looking at like classical probability, but it's important to cover it. So now let's take a look at a bimodal distribution. So in the normal distribution, there was a single mode, and mode just means the most common, most frequent value. But here you can see there's two peaks. There's two values that are very common or frequent. So an example of this would be maybe a sports car manufacturer wishes to find out what appeals to prospective buyers about sports cars. So in order to target advertising towards those desires, they investigate a random sample of like 500 people who have expressed an interest in sports cars. And let's say that 150 respondents indicate that status is an appealing factor. So we could say this is status. And then maybe the other 150 indicate that speed is a really, really important factor. So if you look at this, status and speed would be the most frequent factors given, and they appear with equal frequency. So when those results are charted, you can see that bimodal distribution. Like a lot of people like speed, but a lot of people also care about status, and then there's some other factors that are kind of, not as desirable. Now, it's important to note that this would be a situation where we have nominal data. So the placement of the variables along this x-axis is arbitrary. So you may have the peaks in different positions just depending on where those different factors are placed on the x-axis. Because with nominal data, it's not numeric, so you don't really have a low to high situation. Now let's look at a different distribution, the multimodal or jumbled distribution. And this is when you have results or frequencies that are very inconsistent. So they're just kind of all over the place. You could have a jumbled distribution that looks like this too, just like literally like weird all over the place. So some examples of that would be like numbers of employees in each department. If you have some that are really big and some that are really small and some in between, a lot of variability there, a lot of diversity there. So you'd have a jumbled distribution. Another one that comes to mind would be like if you assess like the favorite book among employees, you're going to have tons of inconsistencies there. So your distribution is going to be kind of all over the place. Now let's take a look at skewed distributions. So remember, the way this works, the height of your line here would be your frequency, right? Higher, more frequent, lower, less frequent. And then you have your variable values from lowest to highest, left to right. So if you think about a negatively skewed distribution, that's a situation where most of the scores are relatively high with very few scores on the low end. So a classic example of this would be any situation where the variable's values have an upper limit and low values are rare. So a classic example of this would be GPA, right? So GPA has an upper bound of 4 and a lower value of 0. And if we think about it, right, with an upper bound of 4, it can't keep getting larger and larger. So if, for instance, the average GPA is really a 3.5, then there's really only so much space to exist that's greater than 3.5 and far more space below it. Another example would be like the price of rent in a rent-controlled area, right? Most prices are going to hug this upper bound, but it's not going to exceed that upper bound because it's rent-controlled and there's a certain limit to how much you can charge for rent. So negative skews are a little bit more rare than the positively skewed distribution, and this is just kind of the flip of that, where you have most of your values fall on the low end, and then you have some rare high values up here. Now, if you have trouble differentiating between negative and a positive skew, I always remember that if you flip this over, it looks like a P, so that helps me with positive. Or you can think of skew as tail, and this tail is on the high end, so you can think positive. This tail is on the low end, so you can think negative. Whatever helps you remember which is which. You can also always come back and look at these lecture slides to figure it out. So some examples of positively skewed variables would be like people's incomes, right? So most people kind of fall, the lowish end, and then you've got, the 1% up there in the top. House prices are the same. You've got most house prices are fairly relatively, on the lower end, and then you've got mansions and palatial estates over here. Another one that really rings true with me is number of accident claims by an insurance customer. I've never had a claim. I've been paying car insurance for a very long time, and I feel like most people are in the same boat, right? They have very few claims, but these people on the high end are jacking up our premiums. Another one would be number of children in a family, right? Most people have between 0 to 3 kids, and then once you get down to higher numbers of children, it's less and less frequent. So although these shapes that I just showed you looked like line graphs, it just looked like that to really demonstrate kind of the shape of the distribution if you traced over all the bars that you have in your data set. You can show data as a line like that, but typically line graphs are reserved for longitudinal data, which will be in a separate lecture. So now that I've showed you the different shapes that can appear, let's look at bar charts versus histograms. And let's also focus on when to use those, and then what do they look like visually, and what are the differences and similarities between the two. So a bar chart looks like this right here, and it is really reserved for nominal or ordinal data. If you are struggling with that, you need to go back and review the lecture on the different types of variables where we talked about nominal, ordinal, interval, or ratio. But just remember, nominal is really just like a category. It has no numeric value whatsoever. And ordinal can be a category or something semi-numeric where you can just place things in a meaningful order, but you don't necessarily know how much of a difference there is between any specific value. Again, you can go back and rewatch that part of the lecture for the different types of variables if you're still struggling with this distinction here. So if you have nominal or ordinal data, you want to display that in a bar chart. And the biggest hallmark of a bar chart is that you have space in between the bars. The bars do not touch. And that space for nominal data represents the fact that you have completely distinct separate categories, as we have here, right? Product type. There's no overlap between Mac and iPad or iPad and iPhone. These are just separate, distinct categories. With ordinal data, those gaps really represent the fact that you don't have an equal difference between subsequent or sequential values. That's not as important as knowing what to display which type of data with. So if you're working with nominal or ordinal data, bar chart is the way to go. So we can see here, product type is nominal. This is kind of like our X here, right? So that's what's displayed along the X-axis. So we've got Mac, iPad, iPhone, iWatch, TV, music, and then other accessories. And we just collected some data to look at how many of each product were sold in a particular day at the Apple Store. So again, you can see that the height of these bars represents the frequency associated with that product. So there was 15 Macs sold. So where you see Mac, you see the bar goes up to a 15. Other accessories, right? There's 56 of those sold, and the bar's height is about at 56. Also remember that you can add up all the frequencies to get the total sample size, total of 163 products sold. Whenever you construct a bar chart, also make sure that you don't just put X and F here for X and frequency. What you should have is each category labeled, and then what the frequency represents, right? And what all those different variables are different types of. And then again, lowest to highest, bottom to top for frequency. And for this, check this out. The order with which you place these categories on the x-axis is completely arbitrary. It doesn't matter. This is not a numeric variable. So shape is actually pretty irrelevant here. You can make it however, whatever shape you want, just depending on how you reorder those categories. So now that we've got this data in a nice table and graph, we can quickly answer some really simple questions about this data. So if we had all these numbers just jumbled, like Mac, iPad, iPhone, just written on a screen, it wouldn't be easy to decipher. But with it in a table and a graph, you can quickly see that the most popular product type today was the other accessories, had the highest frequency of sales. And the least popular were watches. You can see that in the table. You can also see it in the graph, right? Tallest bar, most popular. Shortest bar, least popular. So now let's go back to that data where we were looking at the number of iPads sold in the past 50 days. Number of iPads is our X, our variable. And number of iPads is ratio data. So we shouldn't use a bar graph. Whenever you have interval or ratio data, something that's truly quantitative in nature, you want to display it on a histogram. And a histogram, the hallmark of that is that, see, these bars are touching. Now, it's important to note that interval or ratio data can be discrete or continuous. Remember, discrete means that every value is fixed to a whole number. Continuous means that you can have fractions or decimals in between. So the reason that we have the bars touch for interval or ratio data, be it discrete or continuous, if it's discrete, we have those bars touch to represent the fact that there's an equal difference between subsequent values, right? The difference between 0 and 1 is a 1. The difference between 1 and 2 is a 1, and so on and so forth. For interval or ratio continuous data, we have these bars touch to represent these upper and lower row limits. So this really represents everything from like a 0.5 to a 1.5 right here, and that would be labeled as a 1. So it's just really capturing the full range of all potential values you could have there, fractions or decimals in between each whole number. Again, the rationale is not as important as being able to look at data, make the correct decision about the nature of the display you should do, but I think it's always nice to understand why we have different ways to display this data. So if we look at this and kind of pick it apart, you'll see that our X number sold per day, our frequency is the number of days with that many sold. And you can see again that the height of the bars corresponds to the frequencies. So how many days did we sell 0 iPads? According to this, 5. And that corresponds with this table as well. So if we look at this, right, we could quickly see that, again, on most days, we sold between 2 and 3 iPads, and you see that here as well. Now, it's important to note that for the previous bar chart, shape was irrelevant. Didn't matter because we had nominal data. There's no meaningful order that you can place things along the x-axis. But for this data, we have ratio data, so the shape is relevant, and if we kind of draw a little line above this, you can see it's roughly a normal distribution. So for the most part, selling between 2 and 3, and then we have some extremely high and some extremely low days. But in this, there's really no outliers, so that's kind of nice as well. It's a nice, neat, normal distribution. Now let's take this frequency distribution table a step further. So maybe instead of just looking at the raw number of days that you sold that many iPads, you want to know what percentage of the days you sold that many iPads. So you would want to construct a relative frequency distribution table. And relative frequency is really just a fancy stats term for percentage. So you can see that I did the math in this table just to show you how that works. I'll show you in a separate video how to use Excel to do this. But just so you understand the computations behind it, you can see that we take the frequency for the particular value of interest. That's what this stands for. Frequency for value of interest. In this case, we're interested in the frequency for 0. 5 days had 0. 5 divided by the total number of days, or your N, 5 divided by 50. That would give you a proportion. So 0.10 would be the proportion. To turn that into a percent, you just multiply it by 100, or you just scoot this decimal place 2 places over, you get 10%. Let's just look at the next one. What percentage of the days did we sell 1 iPad? Okay, well, 8 days divided by 50, bam, times 100. 16% of the days we sold 1 iPad. A quick way to check your work on this, if you do a relative frequencies for all of your values, is to make sure that all of your percentages add up to 100%. If you kept these as just p-values or probabilities like 0.1, 0.16, 0.28, then all those values should end up equaling 1. Sometimes rounding error happens and it's not exactly 100%, but as long as it's close, you should be feeling good that you did something right. So keep in mind that although I'm demonstrating calculations for relative frequencies within the table, you really only need to include the final values in tables for reports or presentations. So in the previous slide, you saw all the math, but if you're really going to display this in a table, you wouldn't want to show that math. You'd want a nice clean version of that table with just the percentages. Now, pie charts are typically how we display percentages of a whole for a single variable. So if we look at this, we've converted these into percentages, and then you can display these percentages in a nice, lovely pie chart here, where it's color-coded for the number of iPads sold, and then the percentage represents what percentage of days did we sell that number of iPads. So you can see here, that kind of pinkish red color is for 0, and 10% of the days we sold 0, and bam, there it is. Again, I'll show you how to make one of these in Excel, but for now, I just want you to understand how to interpret it and understand the fact that when you're looking at percentages of a whole for a single variable, a pie chart is the most appropriate way to display that information. So now let's switch gears a little bit and look at grouped frequency distribution tables. So these are really reserved for situations where the data values that you're provided with have a really large range of values. So like income or age or number of sales, like there's going to be a huge range in those values. And if you think about the previous tables I've showed you, every single value from highest to lowest is represented on a row. And if the goal is to simplify your data, if you have a range of 50 values, your table is going to have 50 rows, and it's not going to be very understandable or useful. So grouped frequency distribution tables really come in handy when you have a situation where you have a large range of values and you need to simplify that data by grouping values into different categories. So there's some criteria that you need to follow. I'm going to show you how to do this in a separate Excel video, but you need to know what the starting value is going to be, what the ending value is going to be, and also how much of a width or how wide you want your different groups to be, what you want the range to be for each group. So there's this really cool way to kind of do this without just doing guesswork and doing a table and seeing if it looks good. And this is the 2k greater or equal to n rule. So what you want to do is basically figure out what exponent of 2 is going to give you a value that's greater than or equal to your sample size. So for instance, let's say that our sample size was 50. To figure out roughly how many different groups you would need in your group frequency distribution table, you would need to figure out what exponent of 2 is going to give you a value that's greater than or equal to 50. So we could start with like 2 to the second power, 2 to the third, and see what we get. So 2 times 2 is 4. 2 to the third power would be 2 times 2 is 4 times 2 is 8. And let's see if we did 2 to the, because we're not near 50 yet, we do 2 to the fourth power, we would get 16. If we did, it's down here, 2 to the fifth power, we would get 32. Not there yet, because remember, we need to get something that's 50 or above. If we do 2 to the sixth power, we get 64. Hooray! 6 would be our K in this example. So K would be the approximate number of groups. So you just kind of play with exponents of 2 until you get to the one that gets you just at or above your sample size. Then what you want to do is figure out the kind of approximate group width. So you would take the largest value in your data set minus the smallest value in your data set and divide it by K. So let's say in this example that the smallest value in our data set was a 10 and the largest value in our data set was a 100. So smallest, largest. We would take 100 minus 10 to get 90. Divide that by 6, right, our K, and 90 divided by 6 is 15. And that is already a multiple of 5, so you could just use that as your width. Let's say that we had a sloppier number that we ended up with. Let's say that we had like 14.3. Well, then you'd want to round that to 15 and use that as your width. If you got a width of like 9, then you would round that to 10, right? And you would use that as your width because you want to have an easy to understand width for all of your different groups. So some other rules that you need to follow. The lowest score in each group should be a multiple of the width. So if 15 is your width and you have scores that go from 10 to 100, well, then you need to start with a multiple of your width. So that would be a 5 would be the multiple. And you would do like 5 to, let's see, if our width was 15, then it'd be like 5 to 19, and then 20 to 34. So do you see that? It's going up by 15, right? The next one would be like 35 to 49. And again, you see that the lowest score is a multiple of the width. 5 to 20 is 15. 20 to 35 is 15. Also, you should have all groups be the same width, covering the entire range of scores with no gaps or overlaps. So if you see here, this does not say 35. It says 34 because 35 is here. So you have to have mutually exclusive. Because if this said 35 and this said 35, if somebody had a score of 35, they'd be counted twice. You don't want that to happen. So just make sure that you familiarize yourself with kind of the criteria for a solid grouped frequency distribution table. So when I show you how to do it in Excel, it'll make a lot of sense. So now let's look at another example of constructing a grouped frequency distribution table using the rules that I showed you on the previous slide. So now we're looking at some different data where each of these numbers represents a single Apple store in Australia and how many iPads they sold in the past 50 days at each store. So each one of these numbers that you see represents a store, and there's 20 stores in total. So in this example, our sample size is 20. If we counted how many numbers we have 1, 2, 3, 4, and then 1, 2, 3, 4, 5 columns, and 4 times 5 is 20. So in this example, we know we'd want to use a grouped frequency distribution table because the lowest value in our data set is a 32, and the highest value in our data set is a 219. And if we tried to display that in a traditional frequency distribution table, it would be a nightmare because you would have tons of rows that didn't even have any frequencies associated with it, and the table wouldn't really be simplistic and manageable. So I'm going to follow the rules I just showed you to create a grouped frequency distribution table. So the first step is to figure out K, the approximate number of groups that you're going to use. So if we look at this, we need to have a situation where an exponent of 2 gives us something greater than or equal to 20. So if we look at this, 2 squared is 4. That's not good enough. 2 cubed is 8. Not good enough. 2 to the 4th power is 16. Still not good enough. But 2 to the 5th is 32, and that gets us at or above our sample size of 20. So in this example, we're going to have approximately 5 groups. Next step is to figure out roughly what the group width should be. So you take the largest value minus your smallest value and divide it by K. And in this example, you have 37.4. Remember, part of the criteria for group frequency distribution is to have an easily manageable width. It's something that is could be divided by 2, 5, or 10, right? It's a multiple of 2, 5, or 10. This is not. This would not be fun to work with. So we're going to round that up to 40 because that is a multiple of 5 and 10, and it's going to work out quite nicely. So now that we've figured out the width that we need to have for each of our groups, we need to start working on figuring out where to begin with our groups. So you really want to make sure that you capture the lowest value in your data set, which in this case is 32, and the highest value in your data set, which is a 219. You also want to make sure that the lowest score in each group is a multiple of 40 because that is our width that we decided. So since our lowest score is a 32, we really need to start at 0 to capture that value. And then you want, again, the lowest score in each group to be a multiple of the width. So up by 40, another 40, another 40, another 40, and another 40. And you have to think about it. Okay, will 200 to 239 get me to my highest score? Yes, it will. So I'm done with different classes here, with different groups. Now, what you do, once you go through and you figure out, okay, what are my low ends? Then you just make your high end just below the next low end, right? So 39 is just below 40, 79 is just below 80, because again, you don't want any overlaps. You don't want somebody who has a score of 80 to be counted twice, for instance, if this said 80, which it does not, because that's bad. Also, make sure that you represent the full range of values from lowest to highest, even if some of these frequencies would be 0. And just real quick, to make sure you see how the data corresponds with this table, you can see that when we look here, between 0 and 39, iPads sold in 50 days, 2 stores had that number. So look at this. Here's our 2. These guys with 32, and then this store with 35. And if you want to kind of do it on your own, you can see how all of these values correspond with your raw data here, and it's displayed in a nice, succinct table without tons of rows to show every single value in the data set. So now that you have your beautiful table here, you can answer some simple questions about your data. So for instance, how many iPads should be available in Australia in a 50-day period? Well, if you look at this table, you can see that the bulk of stores sold less than 120 iPads in a 50-day period. So you could say, you want to have at least 120, but you can see that it kind of taps out or caps off at about 240. So you would want to be extra careful and safe and have at least 240 in Australia in a 50-day period. So now let's take a look at a graphic display of your grouped frequency distribution table. And we're looking at a histogram here, where you can see that instead of having each raw X value along the X axis or each potential number of iPads sold here, you have your groups here. So your 0 to 39 corresponds to this. And yet again, the height of the bar corresponds to the frequency. Or in this case, how many stores in Australia had that many iPads sold in a 50-day period. You can also visually see here what we already established is that for the most part, in 50 days, stores are selling fewer than 120 iPads. Now, it's important to note that this is on a histogram because we are working with ratio data. And again, these bars touch to kind of represent the fact that these are equally distant categories from sequential categories. So the difference between this and this is 40, the difference between this and this is 40, and so on and so forth, because we structured our frequency distribution table in the appropriate way. So now I want to show you probably the most important slide in this entire lecture, and this is just a summary of when to use what. So you'll see that there's a yellow line, and I'll even draw it again, around the different, ooh, that's a terrible sound, the different graphs and tables that we talked about in the lecture. And you can see that this just shows you the situation, and then what type of table you would use, and what type of graph you should use as well. So you can look at this on your own, and it's really just kind of a summary of what I've already shown you. But when you go off to do other assignments where you have to make decisions about appropriate graphs or tables to use, this is going to be a really useful resource. And in the next couple lectures, we're going to cover these, and then we will cover these as well. So I hope you find this table useful and you use it throughout the semester and after you are done with the class as well.